So this video we're going to try to sort a data set which is a small data set, not too big. It's going to take too long, so we're going to write our small data set. We're going to try to attempt to sort a data set of 4 elements, and let's write down our indexes because pretty soon we'll know that's important. So we're going to try to sort this data set using SelectionSort. So as we know in SelectionSort, if you've been reading my blog, in step 1 we assume that the element at the first unsorted position to be the smallest. Well, what is unsorted at this point? Well, all of it. So all these elements, pretty much everything, all of this is unsorted. So let us assume we're using some variables and we are saving the smallest position, which is basically, it's not necessarily the smallest position, but it's the position where the smallest value or the next smallest value is located. So let's assume we are storing it in a variable called, for simplicity's sake, so that I don't have to write too much, we're going to call it s_p. I'm going to write it for one time. Let's do this. Position holding the smallest value, and let's assume we're using another variable called FUI, which is basically the first, stands for first unsorted elements index. All right. Also, while we are at it, let's assume that we're going to use another variable called C_I, which basically stands for the position we are trying to comparing against. All right. So as we know, in a selection sort, according to step 2 of my blog, we compare our assumed next smallest element with every other element. Well, initially, sorry guys, I'm trying to get used to this. Initially, since all of the elements are unsorted, our first unsorted elements index is going to be 0. All right. To make it easier, let me write down 0, 1, 2, 3. That's 8, 12, 6, and 5. And our smallest, the position holding the smallest value, let's assume, according to the algorithm, be the first position or the first unsorted elements index. So it's probably easier if I just put it as a box on the side, consistent with our other algorithms, other videos. And initially, only initially though, our comparable index is going to be FUI plus 1, which is going to be 0 plus 1, which is going to be our 1. So that brings us to our C_I, which is going to be 1. So this is going to be our pass 1, and we would be comparing, at this point we would be comparing, let me underline what's our first unsorted element, which is 8, with every other element, and try to find if there's another element which is smaller than 8. So our initial comparison is, let me write the basis for this. So our assumption, our formula for this is going to be, let me write it down. Let's assume all this data is stored in an element in an array called data, and we would be comparing the current index is, if it's lesser than our smallest position, and if it is true, we do a swap. So let's write down our values here. So initially our C underscore I, which is the let's call it current index. Okay, let's call it current index, is going to be pointing to position 12, and which should be, and our smallest, our position holding the next smallest element is 0, which has a value of 8. So if we do the comparison, and we will see the result is 12 less than 8, which is false, so we don't do anything. We move on, and now we update CI, C underscore I 1, and which brings us to the next iteration, which is once again writing our elements 0, 1, 2, and 3. That's 8, 12, 6, and 5, and writing our first unsorted index is 0, our position holding the next smallest element is 0, and our C underscore I at this point is going to be 1. So this point we would be write our formula again, which should basically be data underscore P. So, and our C underscore I, which is our current index, is pointing, our comparable index, if you care, is pointing to, at this point, I'm sorry, this should have been 2. So we're going to write down the value here. Our current index is pointing to position 2, which has a value of 6, and versus our next smallest position we found so far, which is position 0, which is holding a value of 8. And we do the comparison. It's pretty obvious that 6 is less than 8, which is true, which basically means this means we would update our assumed smallest position. So update our assumed smallest position is equal to wherever the current index or comparable index is pointing to, which is basically 2. And we'll do our usual, which is basically we will update C underscore I, which is by 1, which brings us, so that we don't do the mistake like last time, C underscore I is 3. So now the next thing we would be doing is we're going to the next iteration. So let's mark it as this iteration. We'll be doing our next iteration, which is basically 0, 1, 2, 3, and we'll be doing, remember guys, we didn't do any swap yet because we did not yet reach the end of the data set in the last iteration. So in this iteration, however, we pretty much, our C_i reached the end of our data set. So let me write down our FUI is pointing to, let me just write the squares first. C_i and FUI is pointing to 0. That's always going to be the first unsorted index so far. S_p, as we updated it in the last iteration, and it's pointing to the smallest element we found so far, which is 6 at position 2. So we write 2 here, and our current index is pointing to the last element. So that's the last element we're going to compare. That's the element we're going to compare against our smallest element we found so far, which is 6. So our C_i again is pointing to the last position in the data set, which would be 3. So I'm going to write down 3 here, and we'll see where it goes. So we write down our formula again quickly. That'll be data C_i and data S_p, and we're going to change our pen. So C_i is pointing to position 3, which has a value of 5, and data S_p, which is in position of the next smallest element, is pointing to position 2, which has a value of 6. And as we know, 5 is less than 6, which basically means we have to update our next assumed smallest position. So we're going to do that here. We're going to do, this is true. So we're going to update our next smallest position found to be whatever the position our current index is pointing to, which is basically 3. So at this point, we update our C_i by 1, which would be, this means C_i is equal to 4, and since C_i crossed the array, we will end our pass. Perform swap. As we know in our algorithm, step 4 is if we reach the end of our unsorted elements, we have to swap the first unsorted, the value at the first unsorted position with the value at the next smallest element's position. So this basically means we're going to swap. Let's write down the array first. 0, 1, 2, 3, and I'm going to write down our elements initially. So it's going to be 8, 12, as we find ourselves 6, 5, and our FUI is 0, and our S_p is pointing to 3, and our C_i is pointing to 4. At this point, what are we going to do? We would be swapping. Let me use a red color to indicate. We'll be swapping the value at position 3 with the value at position 0. So we'll be putting the value at position 3 to position 0 and position 0 to position 3. So that, let's quickly write down what does it yield us. So this yields, so let me write down swap position 0 value with position 3 value. So this brings us to a result of 5, 12, 6, and 8 at the end of our pass 1. So that's pass 1 over, and we would be marking in our usual style the end of the part which is sorted with an yellow color if you watched my other videos, and this is the unsorted part and this is the sorted part. Now as we repeat our steps, we're going to set our FUI, which is basically the first unsorted index, to position 1, and our S_P, which is the position of next smallest element to wherever FUI is pointing to, which is basically 1, and our current index is going to be, as always, wherever the FUI is pointing to, which is basically 1. So that's how we start our pass 2. Let me write down pass 2. I'm going to write 0, 1, 2, 3, this 12, 6, 8, and our FUI has a value of 1, S_P has a value of 1, or C_I has a value of 1. Sweet, all of them are pointing to 1. So now we would be writing our formula again, which is data being pointed by C_I if it's less than, sorry, this has to be, and that has to be FUI plus 1 initially, always, and so this is going to be, let me write it clean, E is equal to 2, so there you go. Sorry about that, guys. S_P, which is the position of the next smallest element. We'll switch colors. So C_I is pointing to position 2, which has a value of 6, and our next smallest position, which we assumed, is position 1, which has a value of 12, and as you know, 6 is less than 12. We would be doing, we will be updating, which basically means we will update our position of the next smallest element indicated by variable S_P to wherever that C_I is pointing to, which is basically 2. And now, as always, we update our C_I by 1. This means C_I becomes 3. So that's our first iteration, guys. And now repeat it again, writing our array 5, 12, 6, 8. Let me mark the sorted part. That's the sorted part. Everything towards the left of it is sorted. And let me write down our little boxes indicating the variables. If you underscore, that's going to be 1, and s underscore p is going to be 2, and our c underscore I, which is what we're going to compare against, the index of the position which we're going to compare our smallest element against, is 3. So write down our little formula again. Data of c underscore I right, and what's our current index pointing to? Position 3, which has a value of 8, and our next assumed shortest smallest position is pointing to position 2, which has a value of 6. And as you know, 8 is not less than 6. This will become false. So we will not be updating anything except for moving our current index or comparable index to the next position, which would make it 4. And since c underscore I is outside the bounds of array, the pass is over and stu is over and swap is performed. So let's write down 0, 1, 2, 3, and has values of 5, 12, 6, 8, and 5, 12, 6, 8 has a FUI of 1, s underscore p of 2, and c underscore I of position 4. And let me quickly mark our sorted part. Everything to the left of this yellow line is sorted, and so at this point we would be swapping value at position s underscore p, which is pointing to position 2, with value at position c underscore I, which is 4. So this brings us to our next, the result, which is shown here. And let me mark what is being solved. Oh god, again a mistake. So at position FUI, which is pointing to position 1, so we're going to swap this with this and this with this. Okay, so that brings us to the result of 5 and 6 and 12 and 8. And that moves our sorted part one step to the right. So everything to the left of this yellow line is sorted and everything to the right is unsorted. Alright, so that brings us to the end of pass 2, and we move on to the pass 3. Alright, so writing array again 0, 1, 2, 3, 8, 5, 6, 12, and 8. That being the dividing line, our FUI, or first unsorted index, will be pointing to FUI is equal to the previous FUI plus 1, which should be position 2. This will be 1 plus 1, position 2, and our S underscore P will be pointing to wherever position FUI is pointing to, which is going to be 2, and C underscore I is going to be pointing to FUI plus 1, the next position, because we don't want to compare. There's no point in comparing an element with itself. So C underscore I, which is basically the current index, or the comparable index, would be pointing to the position next to the first unsorted index, so we can compare them both. So which would be pointing to position 3. Alright, so with that written, and C underscore I is pointing to position 3, and let's write down our little formula again, which is this less than this. And what is this on the left? Data underscore data that is being pointed by C underscore I. If it is less than the data that is being pointed by our assumed index of the next smallest position. And if we write that down, so we know C underscore I is pointing to position 3 that has a value of 8, and S underscore P is pointing to position 2, which has a value of 12, and of course 8 is less than 12. This means, alright, so it's true. In this case, we're going to update our S underscore P to wherever C underscore I, our current index, is pointing to, which is basically, as we know, where is C underscore I pointing to? Position 3. So it will be position 3, and as always, we will update C underscore I by 1, which basically means C underscore I is going to be pointing to 4. And since position 4 is outside the array, the pass ends and swap is performed. And so that brings us to what are we going to swap. So 0, 1, 2, 3, you have seen this before, but I'm going to write it down anyway. 5, 6, 12, 8, and our FUI is what? Is 2. Our FUI is first unsorted index is 2. Oh wait, perhaps if I draw the yellow line, it'll be easier. So first unsorted index is 2, and our variable which points to the next smallest element's position is pointing to 3, and our current index is pointing to 4. So we'll swap, we will swap element position FUI, which is value of 12 with element being pointed by our found smallest position, which is going to be 3, which has a value of 8. So with that said, we're going to write down what are we going to swap. 0, 1, 2, 3. Just a second, guys, let me be consistent. Okay, with that said, 0, 1, 5, 6, and here is going to be 8, and it's going to be 12. So 12 is, so we are essentially swapping the value at position 2, which is 12, with the value at position 3, which is 8, and that would lead us to this, where our sorted position pretty much encroached the whole data set. And if you read the algorithm, there is no point in sorting anything any further, because pretty obviously the last element would be obviously the next smallest element, and there is no point to sort anything more. So that leads us to our final result, which is 0, 1, 2, 3, and 5, 6, 8, and 12. Alright, so that was 3 over, and that brings us to our result. Thank you.